Let's continue our discussion of salt solutions. Here's a generic representation of a salt. The first thing you want to do is dissociate that salt in water. Treat all salts as strong electrolytes in this chapter. So we have a cation and we have an anion in solution. Whether or not the pH of the solution will be affected depends on whether the cation or the anion react with water. That's the critical step to making that prediction. The cation comes from the base in the neutralization reaction, and the anion comes from the acid. So the anion could be Cl- from a strong acid HCl. It could be iodide ion from hydroiodic acid, which is also a strong acid, but it could be fluoride ion from the weak acid hydrofluoric acid, or acetic acid. It could be acetate. In the case of the anion being the conjugate base of a weak acid, it's going to accept a proton from water and affect the pH. It's going to cause the pH to go up. We'll talk more about that. If the cation comes from a strong base, then it's going to be a neutral cation that's perfectly comfortable being an ion, being a spectator ion in that acid-base neutralization. However, if the cation is the result of a weak base like ammonia accepting a hydrogen ion from a strong acid, that cation is going to be acidic. It's going to want to get back to being ammonia by donating that hydrogen ion to the solution, making the pH go down because the hydrogen ion concentration goes up. So if an ion reacts with water, a pH change occurs. Ions that came from strong acids and strong bases are perfectly stable as the ions, and they're spectator ions. They'll be completely neutral. Ions that came from a weak acid or a weak base will react with water. They will make the solution basic if it's the conjugate base of a weak acid, or acidic if it's the conjugate acid of a weak base. Predicting if a salt is acidic, neutral, or basic. Identify the acid and base that reacted to make the salt. If the acid or the base is strong, the resulting ion in the salt will be neutral. So in this case, I made both HCl, a strong acid, and sodium hydroxide is a strong base. So both the cation from sodium hydroxide and the anion from hydrochloric acid, they are both neutral ions. They will not affect the pH of the solution. They're perfectly happy being ions. On the other hand, if the cation came from a weak base, so here is a weak base, NH3, it reacts with the strong acid, hydrochloric acid, HCl. It's going to pick up a proton from the strong acid. This is the cation that is the result of the weak base reacting with the strong acid. This is going to be an acidic cation, and this will be a neutral anion. Why is it a neutral anion? Because it came from a strong acid. It's HCl's conjugate base, which is neutral. If the anion came from a weak acid, here is a weak acid. This is acetic acid, which is a weak acid. Here is its anion, acetate. And if the anion, here's the salt, this is your salt, and if the anion came from a weak acid, this is going to be a basic anion. Okay, and just to show you the chemistry, this is acetate in water. Remember, what is your first rule when you are trying to decide whether salts are acidic, basic, or neutral? Dissociate them completely. So we'll go ahead and just kick the calcium ion out of there. We don't need to worry about that because it's part of a strong base. Therefore, the calcium ion is neutral in water, but acetate is not. It's going to react with the water. It's going in an equilibrium reaction. It's going to pick up a proton from water, make a little bit of its conjugate weak acid, and then every time it does base hydrolysis on the water, it plucks a proton off of there and makes a little bit of hydroxide. This hydroxide makes the solution slightly basic. Okay, so if the anion came from a weak acid, the anion will be a basic anion. This is a basic anion. It's the conjugate base of the weak acid, acetic acid. If the cation came from a weak base, this is the conjugate acid of this weak base. That makes the solution slightly acidic. Examples. Let's take NH4Cl. What's our first rule? Dissociate it. So that gives us NH4 plus in aqueous solution plus Cl minus. We can just indicate these are in water by putting them in aqueous solution. We could have just also done this. All right, so let's examine the anion first. That's generally the procedure that you follow. And so I'm looking at this anion and I'm asking, what is this? What acid is this the anion of? Well, it's the conjugate base of HCl. HCl is a strong acid, so its conjugate base, the anion of that strong acid, has to be neutral. What base, what conjugate base did this cation come from? It came from NH3. That was the weak base from which NH4 plus evolved in that particular reaction. And the conjugate acid of a weak base is a weak acid. So this is an acidic cation. It will ionize a little bit, and it's going to make a little bit of its conjugate weak base, but also a little bit of this, a little bit of hydrogen ion, which will make the pH slightly less than 7. Okay? And then chloride ion is neutral because it is the conjugate base of HCl, which is a strong acid. Sodium acetate. What's our first rule? Dissociate it. Treat it as a strong electrolyte, which it is. All alkali metal salts are strong electrolytes. It's going to dissociate into C2H3O2 minus. The sodium cation is the cation of the strong base sodium hydroxide. Since this is a strong base, this is a neutral cation. And so we can just classify this as neutral. It's not going to affect the pH. But the acetate is the conjugate base of what acid? HC2H3O2 in that reaction. And so this is a weak acid, making this a weak base. The reaction looks like this. You have an equilibrium. The acetate is going to hydrolyze a proton. It's going to split water just a little bit, make a little bit of conjugate weak acid, and a little bit of hydroxide ion. That hydroxide ion is going to make the pH slightly greater than 7, but only slightly greater than 7. Okay, depending on the concentration of this particular salt. Okay, so step 1, dissociate your salt. Look at the cation, look at the anion. Is this the anion of a weak acid or a strong acid? If it's the anion of a weak acid, then it is a weak base. And the reaction is exactly what we just showed you right here. Okay, look at the cation. Is it the cation of a strong base or a weak base? It's the cation of a strong base, so it's a neutral cation. This is potassium nitrate. And so potassium nitrate, we're going to do the same thing. We're going to dissociate it. We'll just go ahead and plug some water up there. This is an aqueous solution. The nitrate is in aqueous solution. Potassium is the cation of potassium hydroxide, which is a strong base. You really got to know your strong acids and strong bases. Nitrate is the conjugate base of HNO3, which is nitric acid, which is a strong acid. So both the anion and the cation are neutral. These are neutral. They will not react with water. So neutral, I'm just going to say neut and neut. They will not react with water. They will not affect the pH significantly. And so you've got a pH that's really very close to 7. Why do some ions react? Strong acids and bases ionize 100%. They're stable in their ionized forms. Sodium cation, chloride anion, nitrate anion, potassium ion. There's just no driving force to go back to the molecular form. That's in complete contrast to weak acids and weak bases. They only ionize a tiny bit. Why? Because they are much more stable in their molecular form. So there's this very strong driving force. For instance, let's just use fluoride ion here as a specific example. Fluoride ion doesn't want to hang out as fluoride ion. It would be much more comfortable if it could get a proton off of water in an equilibrium reaction, become molecular hydrogen fluoride or hydrofluoric acid. And every time it plucks a proton off of water, creates a little bit of hydrogen ion, which makes the solution basic. So a salt like KF is a basic salt. On the other hand, if you have something like NH4 plus, which we use over and over again, plus water, it's going to donate a proton from water. It's going to make hydronium ion, this stuff right here. It's going to leave behind in this equilibrium reaction NH3. So you have hydronium ion, and you have a little bit of the conjugate weak base of NH4 plus. So you need to take stock of whether you have a basic anion or an acidic cation. Acidic cations come from acid-base reactions where you have a weak base reacting with a strong acid. You also have up here, you have a weak acid reacting with a strong base, producing a salt like potassium fluoride, which can cause the solution to be more basic. And I should have said this is acidic. So where did the salt come from? If the salt came from a strong base, strong bases, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, lithium hydroxide, things like calcium hydroxide. These are the ones you forget all the time. Strontium hydroxide, barium hydroxide. The strong base, know your strong acids, HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. Know your strong acids, guys, and all your strong bases, all the alkali metal hydroxides, calcium, strontium, and barium hydroxide, the heavy alkaline earth hydroxides. What you get from a reaction of any of these with any of these is a neutral salt. On the other hand, if you take any of the strong acids, you react it with any weak base, you're going to get an acid salt, something capable of donating a proton to water. If, on the other hand, you react a strong base with a weak acid, you get a basic salt, something that can accept a proton from water, hydrolyze water to produce hydroxide ion. So any weak acid with any strong base, you get a basic salt. Now, I don't usually mention weak base with weak acid. It could go either way. It depends on the Ka for the weak acid and the Kb for the weak base. You remember this formula, Ka times Kb is equal to Kw, whichever one is stronger. The Kb, the anion that results from the weak base, weak acid solution, or the Ka that results from the weak acid that results from the weak acid, weak base solution. Whichever one of these is higher will determine whether or not the solution is acidic or basic. Make sure you can write the equilibrium that justifies the pH in each box. Okay? All right. And here they are. For an acidic salt, you're donating a proton in an equilibrium. For a basic salt, you're hydrolyzing water.